I'm in Dallas today. Let's talk a bit more about the computers, the way computers work, and let's take this analogy of the meeting, the business meeting, to go talk about a little bit more detailed aspects of how computers work. We talked a little bit about the agenda being on the whiteboard. The agenda is like the programs Excel, Word, whatever it is, Scala, Spark, COBOL, that sits in memory and acts upon the data, a separate type of data. There's two different languages in those two different types of data areas. The data in the computer program in the agenda, it might not be written in what you would think about like the data that sits in a spreadsheet. The terms and the language used in that agenda is specific to the computer processor that it's written on. There's lots of different kinds of computer processors in the world, but every computer process has a specific kind of instruction set, a specific kind of language that it needs to have. That language that's used inside of that instruction set, it's not necessarily the language of the programming language. There's kind of two different languages here. The programming language gets turned into the language of the actual processor itself. So even though I might write something in COBOL or in Visual Basic or in Scala or Java, at the end of the day, all of those computer languages get translated into actual machine code, which is what the processor understands. And the processor can be different on different kinds of computers, different kinds of operating systems. But the key aspect of this that I wanted to get to is the performance of that language. See, if some languages are like the formal language used in Congress, for example, I agree with my esteemed colleague from the neighboring state that we should proceed upon the premise that he has outlined. That is a very long way of saying yes. And so in some cases, the computer languages and the way that gets translated into machine code, those go through very long statements, whereas other ways of expressing that same thing could be done much more succinctly, very short. Because computers have a time aspect to them, computers can do so much work within every second that goes on. There's a time aspect to it. Japanese as a language has a cadence where each syllable is supposed to take a particular amount of time, and that's a little bit like what happens in computers in the way the processors work. So if someone speaks a language that has a lot of syllables to try to convey something, it will take a lot more computing time than if you use a very efficient way of saying something. There's that aspect of also the tool, the way the problem is solved. If someone tried to apply, for example, using a different analogy, someone tried to apply a hammer to put in a screw. Yes, both hammers and screwdrivers place long, thin objects inside of things to hold matters together, hold things together. But the way of working are very different patterns. A hammer has a very different pattern of work than a screwdriver been putting in a screw. Yes, a hammer could probably put in a screw. Might not be real effective, but it could probably do it. I'm not sure that a screwdriver could put in a nail, but maybe. So the pattern of work is important. In some cases, the pattern of work doesn't match the work that the computer has to do very well. It's a little bit like using a very long language to try to convey something. The greater the efficiency of the programming code, and the better that programming code matches what the work pattern is for what needs to be done, that means that the computer will be able to accomplish its work much more quickly. That means you can scale to greater amounts of data, and you can do more things with the computer. It could actually be working on more things at one time. So I think that kind of gets you down to understanding this idea of computer languages and how those computer languages work, efficiency. that goes along with the computer on the agenda on our whiteboard.